Hello, good day to everyone. The TMS320F28379D is one of the latest edition of microcontrollers developed by the Texas Instrument. This is under the C2000 Launchpad family. Considering the fast-ranging features and characteristics of the TMS320, definitely it is a big thumbs up for advanced motor control and design operation. So in this video, I'll be showing you a sample application of motor control in understanding the current response featuring the modulated model predictive current control both in model-based and model-free. To formally start with, we have here the different contents of this presentation, which includes the four parts. The first one will be the discussion of the program code from the CCS, and then after which data saving from the IPMSM operation, and then import the data saves to the MATLAB for simulation and analysis, and then the last one will be the generation of report. So let's open the Code Composer Studio to understand the C language or the program that we have used to run the motor control. This is the workspace of the Code Composer Studio, and as we can see here on the Project Explorer, we have here the active, in which we'll be using the whole entire operation of our motor control. And then we have here the different files, which includes the linker command file, the assembly and other C program files connected to the operations of our main file. But for now, let's be focusing on the main C file of the program. On the main C file includes here the different important parameters for us to operate or to run the system. This includes the variable, the constant, and the system initializations. To start with, we have here the different directives. This is a macro directives, define, and we have here the green part, which these are the constant values. So as we can see here, the rotor speed first command RPM will be set to 500. This one can be set to any values, to any speed that we want to run the motor. And then we have also here the PCC method, which includes the model base and the model free. And the vector size, we have here the 24. This vector size actually represents the number of voltage vectors that we'll be using. And then the DC voltage, which is set to 80. And then of course, once we set the speed of our motor, we have here the KI and the KP gain for our PI controller. So for example, we set to 500, then we have to use this value. For 1000 RPM, then we'll be using this value, and so on. To define our voltage vector, we have here the combined tables, which includes, this is actually 24, but it's put here 28, but it's okay. So we have here the 24 sets of voltage vectors, including their switching states. As we notice, there are three members here, the 0, 0, 0, the other is 1, 1, 1. The first two part here includes the voltage vector, and then the voltage vector combination, and then the last part correspond to the switching state. For example, in the operation later, we're in the combination of two voltage vectors like voltage vector 4 and voltage vector 0, so meaning the switching state is equivalent to 16. The same thing on the last part. For example, if we have the combination of voltage vectors 2 and 4, then the switching state is 24. To define more of the components of our operations of voltage vector, of course, we have to define the sampling time, which we include here as 0.0001, or that's simply equal to 100 microseconds. And of course, we have here the stator resistance and the inductance value. We have also included in the main C file the different prototype functions that we need to run the program. Let's take, for example, we have here the prototype for the EPWM, for the SPI, the GPIO, and others. And also, we have here the different steps on how to initialize the system control. These are the step-by-step procedures on how are we going to run or to collect data based on the operations of our motor. And we are now ready to build, debug, but make it sure that we are running at 500 RPM with command value of 4 amperes. So let's focus first on the model-based predictive control, then after which later we'll be dealing on the model-free. On the building of our program code, this is where we can identify if there are some errors on the programs, and then after which we are now ready to debug. In the debugging, this is where the actual process usually occurs. So once we run the system, so I'll be showing you the video on the actual operation of the IPMSM. But before we take a look on the actual video of the motor running, let's have here the drive circuit first. On this slide, we can see here the setup of the drive circuit in order for us to run the IPMSM. We have here the power meter. This is where we measure the torque, at the same time the speed of the motor. And then we have here the motor itself, the IPMSM, and the drive circuit, which includes the different components. We have first on the letter A, the current detection circuit. We have 2 here because we'll be sensing alpha, beta, or sometimes in the AB because the C can be derived from the A and B phase. Next, we have here the current protection circuit and encoder circuit. And then we have here the TMS320F28379D microcontroller, which will be. And then next we have here the power module or the inverter. And the last one is the DC power supply. So all in all, they are interconnected to each other to run this motor, and this motor will be recorded here in terms of, or we can set here on the speed, and then this microcontroller here, the TMS320, will be connected to the CCS to collect data from the motor. So let's try to take a look on this video. And then after running each of the different method, we can save the data here by clicking on the save memory, and then we can browse on the folder where we want to save. For example, we want to save it on the desktop, and then we can just click here on the homework, and then we can save here. And then always remember that every time we keep on saving files, every time we run on the different methods that we are using, the file format is written on the .dat, meaning these are the data we collected from the operation of our motor. So we have here, we already save here on the 500 RPM 1 Newton meter torque, both on the model base and the modulated model free, or then you can just simply click save on the button. So after we collect the data from the IPMSM operation, we are now ready to analyze and simulate using the MATLAB. So we have to use the MATLAB software to understand data that we save from the IPMSM. So this is the MATLAB program in which we'll be using to analyze the data that we have gathered from the motor operations, both in the model free and then model based. So as you can see here, we have the different informations that are already defined, and then at the same time the path on how are we going to collect the data. Usually this one we can easily graph. It's totally different with the CCS because of the MATLAB will be getting detailed information based on what we desire, if it's in terms of a graph or in terms of other methods that we're going to have. So we have here on the name, and then the other one, this is the root. So on the name part, so we can take this one based on the data. So if we try to open the data that we have just saved, so this one, and you can just simply copy that file here. Let's see that this 501 nm, the 500 RPM 1 Newton meter MFPCC. This is the file name, so you can just write here, and then the root where this file name can be located. And then after which there are different command values that we have saved here. And then the computing mechanism, the computations of error for the ripple, the THD, and others. So to get the data, you can just simply run this one, run the code, and then after which a data will be pop up later. So we have here the figure, at the same time the specific values to which we want to get, like the error at the same time on the THD. But much more onto this one, we have here the figure. So let's try to expand this one, and then we can see here this is the graph now based on the data that we have collected on the CCS. So as we can see here, this is the model free, we have the alpha and then the beta, and then the other one is current error in the alpha, current error on the beta, and then the speed. So if you want to take the other one, so let's just minimize this one. So let's try to change, and then let's copy this file, and then since they are on the same folder, it's on homework, so we will not change this one, and then we can just simply run again to collect the data. And as we can see, we have two folders here. So this one is for the model free, the other one is just model base. So let's try to expand this one and then compare. Automatically also, once we run and then we create a figure, because the output of the MATLAB will be generated an figure. So we have here the two figures that we have created. The first, the model base, and the other one is the model free. So we can see here, so we have here, and the other one will be, so these two figures here represents the two experiments that we have conducted. So we have here the first one, and the other one is this model free. They are both in modulated. However, if we try to compare the ripples on 1 and 2, so if we try to compare the ripples generated on the two methods that we have used, the model based and the model free, it's obviously that the model free has lesser ripples compared to the model based. At the same time, also on the current error generated by the two methods, the model free predictive current control or the modulated model free is better compared to the other. So that's how simple the operation of our TMS320 in the applications of motor control. However, this is not limited to this some example. There are some other methods also that we can apply to this one, not just on current, but also on other parameters that involves in the motor operation.